So the second speaker is, of course, Professor Dipankar Banerjee. I don't think I need to.
You can come closer to the this.
I don't think I need to introduce him. So he'll be talking about the long-term study of the sun using Kodaikanal Digitized archive. So.
Okay, so thank you for this opportunity. In a short notice, because I came to know yesterday, Indranil didn't have a speaker ready, so I volunteered myself. So some of my slides are updated, some are not. So I gave this lecture almost a year back, and Shashi came in when I was almost, the 30th slide. So 30 onward slides are old slides. No, the other ones are also old. Just, at least I've gone through the 30 slides, what are there. So I will see it 30 onwards first time here. So what I'm going to talk about today is primarily our data from Kodaikanal, more than 100 years. And this is the most updated version of the Sunspot area. This is a paper which Sudeep, my former PhD student, who is a postdoc at Max Planck, and in fact, interestingly, Sudeep joined in his PhD program not for Kodaikanal digitization data. He was supposed to do coronal seismology, and he's a very clever guy. In 2.5 years, he had 3 or 4 papers on coronal seismology. I said, your thesis is done. So you can take up a new project. And he started working on this Kodaikanal data. Because of, again, university restrictions, he couldn't submit his thesis for another 2 years, 2.5 years. So in that period, he published around 10 papers. So obviously, Sami Solanki just grabbed him without any application. He was grabbed before even his thesis defense and all that. So since then, he's there. And we are making now collaborative work. You will see this is the most updated version of the Sunspot area. And I think this paper will get heavy citation in time to come. I will introduce this subject, solar cycle. Probably some of you are pretty familiar. The only solar physicist, senior solar physicist is not here. So I still have to give some more introduction about our sun. So what I'm going to talk about is this variation of the solar magnetic activity on the sun. And as you can see from these images, what is plotted here is from early 1600 to 2000 plus, the yearly sunspot number. So sunspot number varies with time. And you see very typically the blue line gives you a regular periodicity about 11 years. So it is not strictly 11 years. There is plus minus 1 year variation. And what is also to be noted is the amplitude of these cycles are also very different. So that's why things are most interesting, that it's just not the periodicity, but also the amplitude are very different. This is the period where the two black line you see is the period where this observation started by Suave. And that's why this cycle is also named sometimes about Suave cycle, discovered in 1843. So earlier also there were sunspot observations, but you can see that there were, I will talk about it, how difficult it is because the observations were very scarce. I mean, only very few locations it was there and all that. So now a lot of AI applications are happening for this period. I will show you that because the density of observations are very, very limited. But of course, there is another big thing which you see here is a huge period, 1650 and 1700. There were no sunspots recorded. Whether it was really there were no sunspots in the sun or the whatever instruments were used to detect sunspots, they were not able to detect the sunspot is a big question. But whatever it is, it appears that with the existing telescope, they were not able to detect it. That means sun was weak. I mean, even if there was been a magnetic field, it would have been less than the threshold of detection, so to say. So why sun became so weak during that? It's not because before that 1650 also people did observe. So obviously, if you compare with the before 1650 and even after 1700, that directly gives a impression that there's something went wrong with the sun solar magnetic cycle, and this is called the Maunder Minimum. And this has a very, very severe implication in terms of the climate. if this happens in the modern day, things will be very, very different. And all our atmospheric science people will jump around. They will get a number of projects to work on. But I don't think Maunder minimum is again expected very soon, because we have now ways of predicting a solar cycle and so on. It is because now what I'm trying to say is that now we have some ways of understanding that what is going to be the strength of the next cycle or the one. So there is also a big question how much advance you can predict and so on and so forth. So it appears the immediate next cycle, we have reasonable good understanding now to predict. So Maunder minimum is not going to come in next 11 years at least. So Manish's period, it is all gone for, because you can imagine if Europe was actually very cold, Volga was frozen for 40 years. Volga River, Russian, thing, were frozen for 40 years. So several thousands of people died for extreme cold climate. So if sun becomes less active, actually it is a cooling effect, which may be not a bad idea in the global warming scenario, but other way, there are a lot of other implications as well.
When sun is less active during the cycle, so do you have any change in temperature here?
Yeah, so this is again a thing which people study. So the atmospheric modelers, they use sun as a constant luminosity. They do not really take, because the forcing in all the models comes as a constant thing. But there is a 0.1% variation, 0.1% variation with the solar cycle. I mean, if you compare, and according to them, it's not a big effect. So there are people who does modeling and all that, but there are secular variations also. If you find that over, say, 70 years, 100 years, there is a pattern of change of the activity and so on and so forth, that may have a more effect than within the cycle. That's the modelers say. But in my opinion, since they cannot still handle that 0.1% variation in their models, they happily take that as a constant. But I think this has to come at some point. It has to come. That's what. So your models are not that precision that you cannot carry about a 0.1% change in the forcing parameter. Basically, it's a forcing parameter, that sensitivity. So that sensitivity changes. Also, what has happened is in the past we knew that this 0.1% variation is actually the total intensity. Now, after the satellite era, now we are actually realizing that the UV flux is changing much more than that. And this UV flux may have much more effect on that. In fact, in Aditya, we have one of the payloads which is going to look at only. And there, this suggestion is that the near UV variation over a long period of time can be even 20%. But you see, the near UV flux in the total flux of the sun is only tiny, because in our optical thing, if you look at the Planck curve, it's peaking at 6,000. So most of your flux is actually in the optical domain. So in the UV domain or near UV domain, it's in the decaying part. So there you do not have too much of total intensity contribution, but the variation is more. So if in the forcing of some of the ozone layer calculations and so on and so forth, UV flux is more important, then that has to be taken into account. But such variation observation for a very long period is still not there near UV. UV is there now, but the near UV, that's why Aditya has one of the payloads which will look at the near UV wavelength. Exactly that period. Exactly that period. Yeah.
Temperature of the world was not decreasing so much, and also that time the winter at the summer at the England was quite normal. So
yeah, there are many theories. So the other thing which I'm not going beyond, before this period, there are now other proxies. You can look at carbon dating data. You can look at tree ring and other data. So that actually field is very different. Yeah. So paleoclimate research, because there are many ICES, not only this one. So if you look at the millennia time scale, then there are 21 such minima. In fact, Arnav also had a paper on this. So from the dynamo calculations, he predicted how many such minimums can happen. If you run this dynamo simulation rather than few hundred years to say 2000 years, then how many such Maunder minima you can reproduce and so on. So, so there are, of course, different, but the available data is so limited. There is room for a lot of different theories as well. Okay, so probably most of you are fully familiar with that, but there are certain elements of the sunspots which we are talking about and their properties, which is crucially dependent with the generation mechanisms. That's an evolution. I will try to emphasize here. So this is a typical image of a sunspot, which is always comes in pair, and you see also this sunspot pair has an inclination. So a sunspot group is commonly known as active region, and active region always have a systematic tilt, which increases with latitude. So this particular sunspot pair is in certain latitude band of the overall sun. I will come to that picture next. And they're always found to have a inclination. This is called the tilt angle. In fact, Vibhuti had a work on tilt angle from space-based data. We're now going back and looking at the data from the Kodaikanal. The other major difficulty with the magnetic activity studies is we do not have a direct magnetic field measurements before 1970s. There were no systematic direct magnetic field measurements at all. I mean, Zeeman effect was discovered and all that occasional but there were no regular instrument which was measuring this magnetic field. So what we have is sunspot. Sunspot just appears as a as a dark thing or in the white light images and so on. We are assuming that is the proxy of a magnetic field. So whatever study happens about the magnetic activity is all based on these proxies. But now how these proxies are directly calibrated with your magnetic field is a big question. So what we assume is that if the sunspot size is bigger, maybe the magnetic field is bigger. Whether it is true or not, that there are big questions on that. So what we have only is information about the sunspot location where the sunspot is formed and the sizes of these. And then again, sunspot sometimes comes in large number of sunspot in a group and so on. So this is called a sunspot group number and so on. So from Kodaikanal, primarily we have worked so far on the sunspot area because we are in the domain, and most of my students only work everything automated way. Nobody is there to manually work on each images and so on and so forth. So we have moved out of that phase. So detecting a sunspot just by looking automatically is quite challenging. So we have not tried to go for sunspot number, because all these photographic plates, when they are digitized and all that, you still have a lot of dust and other stuff. So you may encounter or wrongly detect sunspots. There are also funguses and so on and so forth. So we do a semi-automated method. I will come to that by detecting these sunspots and so on from archive data. Yeah. It's the reference. That's the reference. So which angle you will take? So that is the latitudinal direction. So that's the alpha which we are talking about. That's defined as the tilt angle. So sunspots are associated with region of strong fields, and the polarity orientation is opposite in the two hemispheres. So this is again another information which you have to be careful about. So here I see the sunspot always comes with opposite polarities. You have the yellow guys to the right side of the green guys in the northern hemisphere. But when you go to the southern hemisphere, you see the opposite behavior. So the green fellows are to the right of them. So the polarity behavior and the inclination both are actually opposite in the two hemispheres as well. So this is again an important element which we have to work about. So what we understand is this magnetic field erupts through the surface as tilted bipoles. I'm not going into details about how these sunspots are coming out. So what is now in this movie animation, what is showing is, suppose we have these magnetograms. So these are called full disk magnetogram. And if this magnetogram, now it is a 27-day synoptic map, it's way. So it gives you a full location about the location of the magnetic field. Now, we are running this for 2 cycles almost. So you see at certain period, you have lots of magnetic field, the bipolarities and so on and so forth. So there are many different properties which you see. This is a minimum period where you do not have many sunspots. But then again, sun is becoming active. So you have more, magnetic field in both the hemispheres, and then again it reaches a minimum period. So if I just stop the movie at any particular location, then you will see that there is a pattern of these bipolarities. This is more closer to the maximum period. Then this is more closer to the minimum period, and also there is a progression of these appearance of the magnetic field on the different latitude bands. So this is what we will explain it a little bit in the next slide. So let me come back to why the magnetic fields are there in the first place. So it's a combination of the convection. We know sun is convective, and rotation. And the rotation is also not uniform, it is differential rotation, where equator is rotating faster than this pole. And it is now believed that probably the sunspots are formed at the base of the convection zone. And as they rise up, because of the differential rotation, they are dragged and so on and so forth. So that's the essence of the dynamo theory, which I will explain a little bit more. So there are these elements. If I now zoom up over this portion of the solar cycle from 1975 to 2010, what is plotted here, this is also called butterfly diagram. Inside also, it's a good point. So up to the base of the convection zone, it appears that sun is differential. Then so these all informations we have through helioseismology. This is through the oscillations measured on the surface of the sun. We have information in the deep interior. How deep it is differentially rotating, there is ambiguity about it. So it appears that more inner you go, it is more uniform rotation, whereas the convection zone, the rotation profile is differential. But again, there is a variation with depth also. And that also has a variation with solar cycle. Because otherwise, things should have been all uniform. One cycle cannot be different from the other cycle unless these original parameters which are driving the magnetic field is different. So now we try to understand all these different sources, how you measure it. But again, the point is, it is something interior. You don't have all the information from the interior. From the surface measurements, whether you can get inferences about the interior properties. So differential rotation is one. Of course, the convection is still a big question. How to parameterize the convection is again another big unknown, which goes into the models and so on. So here, what you see is this two element. One is the equatorward migration of the active region. So with the progression of the solar cycle, what happens is the sunspots tend to appear more closer to the equator. And there is a poleward migration of the decayed diffuse field. So sunspot always comes with a pair. So one polarity is going towards the equator. The other polarity, because it is decaying also, tends to go to the polar side. And if you notice here, actually, the polarity of this particular north region was blue in this this particular cycle. These polarities are yellow guys. So these yellow guys will come slowly. They will eat up that blue. There will be flux cancellations. And then the next cycle, the polarity also reverses. So the entire sun, if you see it as a global thing, the polarity flips. Definition wise, probably it is here. Blue is south. So it's a negative. Positive is 10 yellow. So this is, if you really consider a magnetic cycle, it's actually not 11 years, but 22 years. Because you have to explain the polarity reversal also. Apart from the magnetic field strength changes, which is replicated by sunspot number or sunspot area or whatever, polarity also changes after 11 years. So if you have a full-fledged theory, you should be able to explain the polarity reversal and the minima to maxima variation as well. So both these elements are actually very important if you have a full-fledged dynamo. So there are just a bit of dynamo calculations, which I'm not calculations, but cartoon I'm going to give you here to get a sense. What is the current understanding of the solar cycle? Sun has a poloidal field. You see, you have a north-south directed poloidal field. Sun also has a toroidal field. So somehow the poloidal field gets converted, are responsible for the toroidal field, And toroidal field again generates the polarized field. So unless you have a complete loop, you will not be able to, get a cycle repeatedly. So it's like a wave equation. You have to have a, two forces which is feeding one another. So here, what is shown here is this polaridal field. And as I mentioned, that the sun is rotating differentially. So since the polaridal field is, wrapped around by different amount as compared to the equatorial region to the polaridal region, you see slowly you generate the toroidal field. So the toroidal field gets generated by just simply by the wrapping around of the polaridal field, which was straight north-south to start with. Then once the toroidal field is generated, so you have a sort of sunspot pairs. And here, if you notice here, this is a minus sign and this is a plus sign. The plus sign guys, these are the tilted active region, which has been produced by the toroidal field, but then they are decaying. And these positive guys are going more towards the equator, and the negative fellows are going towards the pole. Here, in this particular phase, the pre-existing polaridal field, the pole, was positive. So slowly, these negative fellows will, as I mentioned earlier, will eat up these positive guys, and the polarity reversal will happen. So that's a kind of cycle. But then what happens is these negative fellows has gone all the way to the up. But these fellows has to be now brought back to the base of the convection zone. And that happens through another process called a meridional circulation. So we have something like a conveyor belt inside the sun. So here what you see is meridional flow, which is like this big, conveyor belt. But then again, what is the really structure of the meridional flow? What is the velocity? So in a way, you can say that this is a cyclic thing. But then the main challenge of the meridional flow is we do not have, again, direct observational evidence of the meridional flow. Whether it is a one cell size, whether it is, many cells, and so on. So there are a lot of controversies about that. So from heliosismology observation, people try to, get a feel for the meridional circulation. Earlier, in fact, the original dynamo theory calculations and all that, they didn't have a very precise description of the meridional flow. In fact, Arnab and all these people are famous because of, they could incorporate, meridional flow, effectively in the flux transport dynamo calculations. So, but still the question arises that whether this meridional flow, what you see here is a single cell or multiple cell, or, whether there are multiple layers of these cells. So what is important is this, polaridal fields which were there in the pole, because of this conveyor belt, it will be pulled to the base of the convection zone. And then new sunspots will be generated, and they will be again coming out because of magnetic buoyancy and differential rotations and so on and so forth on the surface to get the new cycle. So what you can again also realize is this polaridal field strength at the end of a cycle is the seed field for the next cycle. So how strong is the polaridal field if the pole allows us to get a handle on the next cycle strength? So this is what the modern day calculations are going on. But then again, there is another thing which is shown here is the turbulent diffusivity. Because convection, how you treat them and all these parameters, in fact, there were predictions for the last solar cycle and had almost from one corner to another corner, from 100 to 350. And in fact, the irony is, Arnab, student Moushumi Dikpati, she had a completely opposite result from Arnab. Both of them were using the same code. But the main problem was this magnetic diffusivity. One had a high value, one had a low value. And that gave completely different. So how sensitive these parameters are, and it made a big controversy in the community. A lot of heartburns, but eventually Arnab turned out, Arnab's calculation turned out to be correct. And so now we have a better sort of feel for the diffusivity. So here, what is shown here is again, this is again, I would say, reproduced polaridal field and toroidal field information. Again, we do not have a direct measurements of the magnetic field. So all these are model thing. In fact, Andres is, work with us as well. And my last student, Shubhamoy Chatterjee, he's now working with Andres in Boulder. So again, Andres came for the IU meeting and just grabbed Shubhamoy, and Shubhamoy is gone. So here, there are two information which is shown here. One is the toroidal field at the top panel. As you see, there is also the north hemisphere and southern hemisphere. You also notice that the behavior in the northern hemisphere and the southern hemisphere is also very different. So this is again something which observation shows, and our theory has to also reproduce it. It's very, very important. And when the sun becomes maximum, your polar field is minimum. And when the sun, the toroidal field is minimum, your polarity field gets maximum, because minimum period only you have the maximum accumulation of the polarity field and so on. So this anti-correlation and all that also has to be reproduced. So that's the sort of, this is an animation then done by Andres. And in fact, Dibyendu takes the credit of, Andres is a big star now. And his PhD time, Dibyendu was actually supervising him in Montana. So this animation, Dibyendu also was involved. Dibyendu is in ISER, Kolkata. I'm also a co-faculty there. So we have a lot of plans to do things together. So here in this animation, you see more or less whatever I was telling in terms of the dynamo calculations. You have the differential rotation, you have the velocity flows by red and blue, this kind of pattern there. And then you see this toroidal field coming out, and they produce the sunspot. So your sunspot number goes up, and then again, it's a declining phase. You have more, polar fields. More polar fields means, open structures and all that. Toroidal fields in the equator size means, it's more closed fields and so on. So this is they're identical. Yeah, I don't think they have. Yeah, there is a few degree angle, but they have, I think, shown these things that doesn't affect too much in calculation. Yeah, because they also are restricted mostly to the lower latitude, because they're mainly dealing with the sunspot generation, which is also a proxy. They don't have a small sunspot or big sunspot difference. Some magnetic field pop up, and that for the solar case, it's all 30-35 degree latitude. So that effect also is not probably so severe. So now I will talk about Kodaikanal archive. It's a unique archive because not only it shows you data from last more than 100 years, it has a multi-wavelength aspect of it, which is not there in any other part of the globe. In fact, of course, Kodaikanal Observatory was built by the Britishers, and famous discoveries were made. So due credit has to be given. There were a lot of collaborations with the Greenwich and the Kodaikanal, because Greenwich observations were more hampered by weather conditions than probably Kodaikanal at those years. So there were actually good coordination between this, and the famous Evershed effect was discovered. So Mickey Smith, Evershed, these are big names who were there in Kodaikanal. So no wonder we had the best instruments also at that point of time, if you compare with the globe. Then another interesting aspect is somehow this is the only place the instruments have not been modified over 100 years. I do not know, because of lack of money or which is good, which is very good for a log data archive, because many other places they could not do that actually. A lot of places have discontinued after 70s or mid 70s. In between, they have also changed certain elements, right? They change a filter, but that filter makes a big difference, because your bandpass changes. You are really not looking at the same atmosphere anymore. I mean, you guys will understand. I mean, if you are making a chromospheric observation, 0.35 and 0.5 angstrom makes a big difference. So for a consistent uniform data, your optics and weather conditions, uniformity of the weather conditions are quite crucial. Unfortunately, the weather conditions uniformity has been hampered. We'll see from our results very clearly. And the other thing which I wanted to also focus here is that it has so if we just go back to 1958, 1st of January, and I look at the archive, you have a white light image, you have a calcium image, you have H alpha image, and there is also a prominence observation by blocking the solar disk. This is quite a unique observation which is not there anywhere for such a long period. It's the only data source throughout the world where separately prominence data is there. So, so this is a long period over which these data exist. This has all been digitized with a lot of is the prominence. Yeah. So the solar disk is blocked. and you see these features, their prominences. And in fact, you see two dots and these things. These are the north-south pole marking. So there are a lot of work from the raw data to the calibrated data. I will not have probably time too much to talk about it today, but quite detailed calibration process is involved. And I think over the years, now more recently, we have understood or improvised a lot of new techniques, which is allowing us to look at this kind of data, which are quite tricky. So this data is open for public for quite some time now. And in fact, I'm happy to note now that there are more papers coming from abroad than in India from this same archive. In the past, it was not happening because people didn't have access to the data. So this is the top building in the Kodaikanal Observatory. And you see this dome where there's a 6-inch telescope, which is looking at the sun from 1904. Even today, I think there has been an observation taken from the same telescope. And we are taking this thing in X-ray films now, because photographic plates are not available, films are not available. So there are some films they get sometimes 10 years of continuous observation, because it's very difficult to get those films. But for archiving purpose, we are still taking that. So one boy, he still wakes up in the morning and takes an image with the same telescope by almost like the rope and by hand and things like that. There's no automation there. So he still covers with the black cloth and takes it. So Manju has also a lot of experience here. So Manju is a postdoc on this project, and he has a good amount of experience in this. Although his PhD was not on this subject, but since then he's working on this digitization program. So I will not go into too much detail on this, of this image processing, how we go from the raw image. This is what you see there. And no, film. So you have to then again take it to the, your digital device and take a picture of that, and then only it becomes a CCD image. Before that, it's all, photograph. So we are luckily getting it. So from abroad most of the time, but we get in a large volume, so it manages for 3-4 years, and then again when the quota goes low and all that. So Kodak, I think, is still supplying us. No. It's a CCD camera. So we have a 4K by 4K CCD camera. So the digitizer work in a way. So we have a huge ball of light source. We have lots of LEDs and so on and so forth. And then there is a small little window at the top where the light comes out uniformly. So this is like a lap sphere. And then through this process, any other scanners will not have such a uniform light illumination. So less than 0.1% kind of, they've been tested and so on. So you have this window. So you place the film on that window, and then you have a CCD camera, which is cooled at -70. These cameras actually costed 1 crore about 10 years back. Very good quality, low noise CCD cameras. So it takes a picture, and then of course you have a digital image, and then do the processing.
So how many extra films do you spend per day? Just one?
One. Yeah, now that is your archival thing. One image.
But
So
daily we do.
daily, whenever there is a clear sky, he will take a picture. So his job is that. So, I mean, the boy who is there in the digitization lab. So the digitization lab is in the same building, actually. So, no, ideally he should take it in the morning.
Okay.
So before the breakfast, he takes it, because that's the best time for the solar observation also. In Kodaikanal, weather goes bad. That's right. So here I was just briefly mentioning about the semi-automated method where these sunspots are automatically detected, and then the sunspot area is just recorded by number of pixels, and then you convert it to some units and so on. And this is what is maintained in this particular table, which is now there in ARIES and CDS data sources also. They were very happy to take all this data, because one thing is, the images, but not everybody will be able to extract information from the images. So what you extract the information to make those data available to the community is also an important element. So that's why you also get good citation of your papers and so on. So this was our first Sunspot series, which Sudeep did for the last 100 years. And then, as usually, as I mentioned, Greenwich is the source which globally considered to be the standard candle. You have to compare with your Greenwich data sources. Incidentally, Greenwich actually has collected data from all over the world. It's not that it's only data from Greenwich alone. So they have done, a collection of things, including Kodaikanal. In fact, incidentally, somebody from Greenwich wrote to me that we have this Kodaikanal plate, what do I do? And I have no clue that they had this. There's no record, no documentation. Through some individual collaborations, data has gone. And these people say, oh, we do not have space, boss. Please take it. So I had to pay for the freight charge to get back my data. So. Yeah, so since you asked this, so as you rightly pointed out, so quasi-periodic oscillations are also there in this. So this is, I think this is a monthly data. If you look at even the daily data, you will find more variation. So in fact, we have that in one of the papers where we have looked at other periodicities present in a solar cycle. So the 11-year, as you can see, is the most strongest period. But other periods also is some manifestation of the dynamo only, which the flux transport dynamo still cannot fully explain. But there are other quasi-periodicities from several months to 1.3 year. 5.6 is also comes because of the polarity and all that also it comes. Then 22-year periodicity is also there. So there are other periodicities which comes out of this. Yeah. But the thing is, in the normal power spectra, your power is so strong in the 11-year, unless you suppress that, you will not be able to, see the other one. It comes, yeah. But now there are much better techniques. So we do wavelet, we do EMD analysis. So EMD will give you, automatically all the other, periods present as well. So the windowed wavelet transform also will give you that. Yeah. So we do all that analysis. So we have a publication just on QPS also. So what other thing which we are looking at actually now or focusing on, and Sudeep is doing that exercise, is there are also different colors in this sunspot which have been depicted here. The red ones are the biggest sizes, and the blue ones are the smallest sizes. So what you can notice here is that the big guys are always looks to be at the low latitude, and that happens during the maxima only. Whereas the other sizes are distributed all over. Now the question which comes naturally is the big guys and the small guys are generated by the same mechanism or differently? So this is a question which the dynamo guys cannot explain because they do not have a difference between a small guy and a big guy. But in 3D simulations, these elements are coming out now because I will explain some of the new features which is coming. So this is a new output from Sudeep, which is going to come probably this month sometime, where you could see that he has combined 13 observatories now and cross-calibrated the data. See, what was important was, you see, people were working little isolation. Like, you have a Kodaikanal series, I have a Mount Wilson series, I have a Italian series. But how to combine this data? Because every places you have some data gaps. You have certain problems in your data series or for certain period and all that. And when you have a data series somewhere and the other data series, is it possible to just, place it one after another? May not be, because their instruments are also different. So you need a proper calibration mechanisms where you can scale these things. So it's a very rigorous exercise in this paper, which Sudeep has done. There are very important people involved in this. So this is, so Sudeep was tracked. In fact, Nimesh was my project student many years back, who is a PhD student there. Natalia is the person who works on the climate stuff. She has 3 science papers. Sami has 5 or 6 nature paper, just on irradiance studies. So the irradiance guys, of course, they need data and well-calibrated data from different sources. That's why they were very keen to collaborate with us. So now you see they're really a completeness that these big sizes of the sunspots, they really have, a very fixed pattern of their, locations and their variations with the solar cycle and so on. There is another property which you see, I will talk about it probably briefly later on, is during the maxima, there is a double peak behavior, right? So you see something coming up, then it dips and then again goes up. So this is called the double peak nature. Again, dynamo or normal theories were not able to explain this. We have a new paper on this with Vidya. This area of the sunspot. So what happens in a particular day?
Total number of sunspots you see, or it's just
it's a total sunspot area. So I'm just let me explain. So suppose in the single day you have one sunspot here, one sunspot there. So you just add up all this, because that also gives you a measure of your magnetic flux. What I'm trying to say is, in fact, in my opinion, the sunspot area is a better proxy of magnetic flux than the sunspot number, because you may have many sunspots, but they're all small. So if they're small, that the overall flux is actually less. So number may not be the best, measure of the magnetic, property of the sun. So that's why I'm particularly in that domain where we are looking at the sunspot area. So we have binned it in different sizes. Huh? So the small guys are those who are greater than 1,000 hemisphere sizes. Then the small guys are less than, So you need to have that information also. So we are keeping that information. We are storing that. Otherwise, you won't be able to also plot the butterfly diagram, because you have each spot, you have the location in the latitude, longitude as well. So all that is also necessary. So those informations are retained in this plot, but in that it is all summed over. Yeah, so it could be one also because of the sort of lack of resolution, or you will see that how much data we have in the current say 50-60 years as compared to the previous domain. So the resolution basically also brings in all these details to some extent. Well, you know that since you asked this question, that it is not always necessary that it has to be in the maxima also. This is what we have theoretically now proven. You see this guy here. You see this guy there. So now we have found out a different source of that. So I will talk about it very briefly. And then, as I was pointing out again, I will not have probably time to go for each paper, because they're all individual papers actually. But I wanted to sort of emphasize that from the Kodaikanal archive itself, we have been able to work on many different properties of the solar cycle, which needs a separate theory to explain. Because this is what the observer's need is. Observer has to put the challenge back to the theory guys. Boss, you have a theory which explains certain properties of the solar cycle, but it still doesn't explain many properties. What about those? Please, go back and work harder to explain that. And in fact, I'm lucky that way. Since I have some, early theory exposure, I'm able to work with Arnab. I'm able to work with more Arnab students. And we have many such work. In fact, Vibhuti, Manju, they all interact with, these modelers now, because that's important. Otherwise, it's dry actually. So because you need to have an explanation why this is so. It's not only important to show that, there is a difference between North and South. But I would not be satisfied with that unless your interpretation is sound with some theoretical explanation. So here we worked on that North-South asymmetry also has something to do with. Incidentally, we have a Indo-Russian BRICS project. So this paper came last year. Leonid Kicharinov, he works on, it's a big name actually in convection. He does for stellar convection and stellar dynamos and all that. So Leonid was very much interested. So we initiated this. We were supposed to have next week the BRICS meeting here, but we couldn't host it this year. So there is a theoretical work on this particular paper, which is done. There is one more later article which we wrote. Again, Sudeep spotted this. I mean, the students have to spot these things, and I didn't spot that. he only spotted it and came back, and then it was just 2 weeks walk, one later. Basically, what it is showing is here, if you notice, is the top panel shows the sunspot solar cycle with all sunspot area taking together. Now, what I'm doing is progressively, I'm taking the smaller guys and then the biggest guys as we go down in the panels. So what you see here is that if I take all the sizes together, 19 cycle, we all know that 19 solar cycle was the strongest cycle of the last century. There's no ambiguity about it. But if I just take the smallest ones, then it's not the 19th cycle. Interestingly, it is 21st cycle, which is much stronger. Then progressively, if you go only to the bigger guys, if you just pick up the biggest sunspots, then actually that mimics exactly with the overall picture. In fact, the biggest sizes dominates the entire scenario. The small guys are actually neglected that way. You can jolly well neglect it and do your calculation. But then the big question comes, are the small guys directly linked with the big fellows? Are they generated by the same mechanism? So then what we did, we tried to look at the distribution of their sizes and so on. And there are a lot of theoretical work which explains this. They're in the nature as well. Why do you see different sizes, scales? All these scales is it just by a colmograph stuff? I mean, nature, anything you talk about, right? So here, from the Kodaikanal data, the problem is this, because we can't really detect very small sunspot because these are digitized images. The resolution is limited, and then you are still reading by a CCD, which has a 0.6 pixel, 0.6 arc second per pixel resolution. So that limits the observability of the smallest sizes. So if it is a log normal distribution, is it it tips like this, or this is a real big ambiguity now in the entire community. That is that a process called fragmentation, where the big fellows are just getting fragmented to small ones, or small ones are getting collated. So it's a number density, yes, by the area. By the area. So you take it, calibrate with the area itself, so that you get a log normal distribution. But it's not, as you see here, that most of the data points are in this area, and this area is very problematic. And since we do not have a handle on this, we will do this exercise more with the modern day observation. But unfortunately, even the space data, in fact, Manju and Vibhuti was also looking at, we have not been able to go too far in that domain. So maybe in near future, this can be addressed. But this is an important element in terms of the origin of the sunspot, because since we find that the statistics of the distribution of the sunspots are different in different cycles, are the small spots are generated by a local phenomena? There is a bigger question in the solar case, is that maybe in the sun there are two dynamos. One is the global dynamo, and one is so-called surface dynamo. The surface dynamo maybe, which is happening only the very shallow layer of the convection zone, may be responsible for generation of the small scale magnetic field, whereas the global dynamo is probably responsible for the big large scale field generation. So still there is no, because the small scale dynamo is not incorporated in the standard flux transport dynamo. It's only the full 3D MHD simulations will be able to answer. But still we are far from achieving that. But there are indications that probably there is a surface dynamo which is also existing. So this is what I was referring to. We have an explanation of this double peak. So what it is shown here is, if you just plot the combined data of sunspot, then you don't see it that much. Basically, when you also split the north and south, then you see it more. So there was one argument that because of this asymmetry between the north and south, that gets, when you add them up, that shows some, some kind of, result in the peak. But then it was, as I pointed out earlier as well, that it's not that it's always during the maxima only. It is also possible in the lower period. So what we discovered, because again, the magnetic data is not there for a very long period of time. So this is the longest period of magnetic field data which is available of such resolution from the ground. So from 1975, what is plotted here is the red and blue is again the two different polarities. And as I showed you before, this is the equatorward migration of the majority field, and this is the poleward migration for the weaker field. But occasionally you see that these are all blue guys, but suddenly there is a strip of red fellows. Again, in this, they're all red fellows, but suddenly there is a small little blue fellow.
But these are all polarities, right? So,
these are all polarities.
So the red is probably from where the magnetic is coming out. The blue is where it is going down, right?
Yeah.
So are the streak, the red streak and this blue stuff not there? Are they related? All those?
No, this is showing pictures of very different times. It's not in the same time. Huh? They're separated by months almost. During, say, 1 month period, it's only one particular polarity, the diffuse field is going. So that means this Hale polarity law, which we were saying that they're in the tilt, and the top guy should have a negative polarity and this guy will have a polarity, that is not always 100% maintained. These are called rogue, so it's flipped. So these are called actually rogue sunspots. This has been a new name now. So they are not normal, they're abnormal guys. And in fact, no, it will be always two on an average, because you can, because sunspot doesn't really always come in one pair. There could be a number of sunspot in an active region. But when you average out, you will find one polarity in the top and the one polarity in not. What it means is somehow when these sunspots were coming out from the surface or subsurface, there was some rotation or something which is made is magnetic energy, and they give rise to huge explosions and so on and so forth. And this is what is seen here as well, that whenever you are finding that kind of, so this red streak, if I now look at, that is actually resulting into this small little change in the polarity field, because the polarity field is either growing or so here in this case it was growing, but since opposite polarities was so there is a little bit of dip, and then again it goes up when after a month or something the normal kind of sunspots coming. So that gets reflected in the next cycle certain time. So we are even actually, this is a very big modeling happening. Mostly is doing that with us, predicting periods over which you will have big flares. Can you predict, say, 5 years in advance or 4 years in advance that there will be a period over which you will have lots of space weather effects? So there's a big game. A lot of money is getting in here. But then, your ground-based observations already giving you some indications that corresponding to this period, because there was a fluctuation, that will get reflected in the next cycle sometime in future. So there are models which is happening. Maybe sometime I will talk about. So a summary of white light data, because there are 4 types of data. I'm sure I will be able to complete all of that, but whatever it is, I will cover, and then we can take it up later on again. So we have, although we have more than 100 years of data, there have been some challenges. There have been small changes in the early period, because this setup had, some modifications were done and so on. So there are some challenges which, Manju and Vibhuti is now, facing, and we are working on those stuff so that we have the full digitization of the last phase of the data, 2012 to 18. This is also actually complete. As I said, this is a 1-year-old slide. And then there are quite a few papers which has come. In fact, what we are doing is, apart from the Kodaikanal data, as I was trying to indicate, we are looking at data sources from multiple places. We are doing cross calibrations. We are into quite a few international collaborations. What Vibhuti is also doing is now merging with the space data. So that's again another set of challenge, because the way the ground-based data is collected and the space-based data is taken, their resolution, their quality is very different. So now that is also one effect. This hopefully will submit in very soon. The last line which I wrote, variation of differential rotation with solar cycle. Vibhuti has done few things with the MDI and HMI. These are the two magnetograms and things. I have not included those lists. So hopefully you'll give a talk sometime. The tilt talk you already gave, right? Magnetic tilt, there was a seminar on this. Oops. This is the current state from Andres Muenes. What it is showing is the density of data or sunspot number. So Andres does work. So you can see that how sparse, so how many observatories are involved in this period. So this is, 1950 onwards. They are really a little bit of scatter, but if you go to the historical time, then it's really, really sparse. So, so accordingly, the sunspot number series, then this is the butterfly diagram. And as you can imagine that you have really, limited information. Now, Andres does a lot of artificial intelligence and all that stuff. So he is into this job of trying to reconstruct in the best possible way this older stuff. So for that, what they do is they, of course, train the data, they train the series and so on and so forth for the current 150 years or so. And they try to go back in the history. And they have a way of verifying whatever limited data they have with that, that period. So that's the thing which they are doing now. Shubhama is involved with that. Now I get into Shubhama's thesis thing. Shubhama was hired for designing optics of soot instrument in Aditya. So he spent first couple of years, majority of the time in Ayuka actually. You see, the other thing was this kind of data which are of historical value. The modern students, they don't find exciting at all. They said, like, yeah, old, what's late, like, it won't come. I mean, this is too much. So I didn't actually propose any PhD because, you have to submit a PhD proposal and all that. So I actually only utilize my, my good resources to give them as an additional work. And I must tell you, Shubhama and this guy, Shudip, it was their second project. It is not there in his thesis at all. There is not a single chapter in Shudip where all these paper, what I was talking about is there. Of course, he got the postdoc based on this now. But now I'm asking him to now, 2 saal ho gaya, fir go back to coronal seismology. Ye kafi ho gaya. So, I think that flexibility is very important for the students. So similarly, Shubhama, he's fantastic. He's from a engineering background. He's a IIT engineer. Then he came through our MTech engineering program. But his mathematical skills were so good. Whatever new ideas I have, he just coded it and just started working on it. I had no skill like that, on coding, or I just only give them ideas. But the implementation things is amazing what Shubhama has done. Okay, so the series, we have large volume of data. But as you see from this plot as well, that beyond 1980, the number of images are reduced. This is a direct implication of the Kodaikanal weather. I do not know about the observer. I don't want to comment, but but it is also true from the just looking at the logs and the painstakingly the way the data has been stored. The people in the past had a different kind of motivation. It's amazing actually. Patience. They didn't think about anything else, and they were not bored easily. I think today, probably we have too much distraction. We get bored about repeating exercise. It's the same exercise they have to do painstakingly, right? And I think those people never thought about those things. They were not coming into their mind. Same exercise, painstakingly they were doing. So the consistency, it's amazing. You will think that the older the plates, the quality is poor, right? Ulta. It's exactly that. It's ulta. We have fantastic data up to this period. Then the data quality is bad. Of course, it has to be something to do with the atmosphere as well. The Kodaikanal weather, industrialization, the sky and all this. But it's quite amazing. And even the quality of the photographic, development. See, these are our photographic emulsions. So you have to still develop in the dark room and so on and so forth. So those process, the chemicals which are used, maybe everything was too pure those days, because it's unbelievable. We'll think, oh, the old plate तो उसमें तो काफी fungus होगा, ये होगा, वो कुछ है ही नहीं, कोई problem ही नहीं है. It's amazing. Only dehumidifier was used in the preserved room. Yeah. No, you see, this is another interesting thing. So it is reasonably preserved pretty well. So they're all in wooden boxes and so on and so forth, in a dehumidifier environment and all that. So they've been properly stored, I would say, with all UPSs and all that. So certain conditions, although it is in Kodaikanal, so much of rain, it's very similar to here. You get in the rains and so on and so forth, but it's quite amazing. Quite amazing. Yeah. Well, that is true. So that was one of the main purpose for doing this, that, for prosperity, you just do it sooner than later, because it's true that some deterioration will be there. But that's what I wonder, that the chemicals were also probably very good at those times, that the deterioration, what you are saying, is not so prevalent, particularly surface ones and all that. I mean, one thing is there, which I didn't talk about it too much here, is when you have something in, say, 30s and when you have something in 70s, in terms of proper intensity calibration, it's a big challenge. Because what you are doing is you are converting from density to intensity. So depending on your number of photons, it penetrates to different depths in the photographic film. And that, depending on, again, the dynamic range of those films and so on and so forth, you have a scale. So there is a intensity scale. So they have taken this kind of, scales on 50s. Unfortunately, that is not there in the past, before 50. They realized that that will be necessary when to convert from density to intensity. So this is a big challenge. We are doing some other modeling method, mathematical models, which is allowing us to do the density calibration, density to intensity numbers. So here, in the first phase, what we did is only identifying features. There, it doesn't matter. It's a relative thing. You need to know the boundaries. You have thresholds. You have different, parameters in terms of, even detecting the disk. You apply half transform, circular half transform to find out the edge. You growing, some schemes you can use to see the sizes. You can give a size criteria. So there are all these, things have been incorporated in this.
Recent data, like last 2020, was there like a special reason for this? Or...
Yeah, importance were I must admit, importance were reducing. Incidentally, this is like almost a frank story. I was never involved in this. I mean, I'm trained in theory, and then I've only worked with space data. After I came back to India, also I was continuing the same way. Some modeling, some space data. All this archive development was all due to Professor Jagdev Singh. So he was doing that. And things were happening for a very long period of time. So with all fairness, I would say that in the past, I think the closure is always a problem. All projects continue forever. I never see the end of the light at the tunnel and so on. Unfortunately, he retired, and then director called me and said that, Dipankar, you have to take over this project. I said, I have no clue about long term. I only look at minutes variation or hours variation maximum. This is a much too different subject altogether. And I do not know the instrument also, that to be fair. So it was quite a bit of challenge to, get into the project. And so that's why I never took a PhD student initially to work with it. Now I have a PhD student dedicated for this. But I didn't have that. So that was a problem with the senior people also to continue with this similar kind of information, because there were not that much result coming out. Unless you, at the end of the day, you publish, otherwise you perish. This is the modern day thing. So I'm happy that this database people talk about, globally they talk about. And of course, credit has to go to Professor Singh, because he initiated that. I only completed it. I take the credit of completing it and making the data available to others, which was not in the mind of, I had lots of resistance of making the data public. Anyway, so that's how it is. But these are really gold mines. So it is important that this kind of data is available to others. And then, bright young guys like these guys are now working on this, which was not, and always the complaint was also in the past that मुझे तो student नहीं है, आप student है मैं result निकाल दूंगा. The student लाना तो, I mean, you have to attract students. I mean, institute cannot, give you student. So that was, earlier director's problem also, to be honest. Okay, so I think what I will do is I will skip, 3 other series because it's already 1 hour. I will just get to my last 2-3 slides where I talk about a little bit on the data archiving and all that, because that may interest some of you. I will come back and talk about, because the calcium data is one of the most demanding data in the world now. I mean, this is the most valuable data. So I will skip these slides. Sorry about this. I love talking about, but this is a general thing I have. So I'm coming to my last few slides. So yeah, since you asked the question, so that's not the same. These are spectroheliograms. So these are not standard, single telescope domes and so on. So the spectroheliograph observations have stopped. But for a continuity sake, again, thanks to Jagdev Singh, he set up a twin telescope with the white light, tube and the calcium tube. But again, in more recent time, what has happened is, challenge of, keeping all the instruments functional every day and all that. This is my problem. Because if I want to do something, first thing I would look at is the reliability of an instrument. Because these are synoptic data. It is so much important that you have every day one image, right? At least, otherwise you can't do that science. So these telescopes again work for some months, then again it goes bad, again works. So that is not useful of this, unfortunately. So there are a few facilities. Now with the current new generation, they're trying hard, and some of these instruments are getting back on track and back online. So we have now more regular observations. But I think this is the challenge. I mean, I'm just very frank, if the H-alpha telescope is there. I mean, if there is tomorrow a flare, I mean, you have to observe every day so that you catch the flare, right? You can't say, oh, flare jab aayega tab jaake chalu kar dunga. Ye to nahi hota hai na. So this is, for solar observations, reliability is very, very important. I mean, any observation for that matter, but for this kind of work, it's a synoptic of work, forget about all the, complications and all that. You just take one image, simple image. So वो 100 साल से पुराना टेलीस्कोप से अभी एक इमेज आ रहा है, नया टेलीस्कोप से नहीं आ रहा है. So that is not, the right thing. So you see, these are very robust systems, so to say, because you have a cellostat arrangement, and then there is a slit which moves. It scans the, entire solar disk and takes the image. But since the twin telescope was, you also have to have some, somewhere to defend. Why did you get a new telescope? Because you want to phase out this. It's very difficult to get films and so on and so forth. So get rid of the spectroheliograph, have a default, one image, multiple wavelength. So you have calcium, you have H-alpha. There is a good H-alpha telescope now, which is functional pretty well, not only in Kodaikanal, also in Merak. So both the sites, the H-alpha observations are going on, but the calcium is not regular. There is a new telescope which was originally done for white light that is taking some observations from calcium. So I do not know how regularly they are able to take it now. Warm le raha hai na? They are taking it. So it's again been, some new people have come in and so on who are taking responsibility of this. So what I wanted to emphasize that this is one of the unique aspects from Kodaikanal data, that it has simultaneous measurement 3 wavelength bands, which covers this white light, I have not talked about these other two wavelengths at all today. So what you see here is the butterfly diagram from white light, butterfly diagram from calcium, and this is a butterfly diagram from H alpha. So there are different elements or information from these, because sunspots are only the strong magnetic fields, whereas the calcium has also representation of small scale fields. Filaments actually follows under the polarity inversion line. So you have three information now. You have the strong field concentrations. You have, of course, all strong field concentration will show in calcium as well. But additionally, you have information about the small scale field all across the sun. On the top of that, you have also information about the magnetic polarity lines. These magnetic polarity lines are very important information. And when you go to the poles and so on and so forth, those long filaments which are there in the pole, they are directly linked with the polar field. So there are lots of information. I mean, huge amount of data. I mean, I can guide, easily 4 or 5 PhD students any day. Okay, so so white light is photospheric. Yeah, so it's 5,500 or something. Where is the central thing? Do you remember? Okay, yeah, probably slightly higher than. And then calcium is, our calcium 2K line. So it's a, since it is a slit thing, yeah. Okay. So that's precisely on the calcium 2K line.
It will be probably a little poorer in terms of feature resolution because it's a bluer side and the green one is selected.
Yeah, so it also depends on, of course, there are a lot of elements which will decide on your feature identification. Is your slit width, your seeing, because most of the time, most of the time in Kodaikanal, we are actually dictated by seeing, if not anything. It's not the optics, but the seeing which basically dictates what all, how precisely you can do it. So we can measure, and the CCD resolution also is a big point. So it's 0.68 arc second per pixel. So typically I would say, 1 arc second size kind of thing. So these, since you asked this question, you see in the network boundaries in the calcium, in the chromosphere, you have these network bright points, which is now considered to be the foot points of the small flux tubes. So that's how you have information about this small flux tubes. In fact, we have done one work which is pretty well done, Shubhama has done. Even the size of the network cells, we can have an idea. Because calcium shows you the spatial distributions of the cellular sizes. And this size is actually changing with the solar cycle. Because you see, the magnetic field provides a rigidity, whether the cell size will be this much or that much. So there is a full-fledged work, what we have done. Pretty a little debatable because we don't have a direct magnetic measurements at that point of time. But we are showing that there are lots of different spatial scales we are finding in the network structure. This has a direct implication of the convection theories and so on as well.
If you sort of whatever modeling you are doing to sort of estimate the magnetic field, right? If you do it in an era where you have good resolution.
That's what we're doing, exactly.
Okay.
That's what exactly we do. So what we do is, so you have a period, say 75 to current period, you have magnetic information. So during this period, you cross calibrate and find out the calibration factor. So if you can find out that calibration factor, the period over which you do not have a magnetic field, you infer the magnetic field in that period. But then your intensity calibrations and all that also has to be very good, because how do you know that the data which is in 30s and 70s are comparable? So that also has to be, put it in the same platform now. So these are the challenges which is there. So this is again, a lot of questions are there, whether they fall a power loss, a distribution, or there are, natural, the convection theories, whatever they say, that there are preferences over, say, mesogranular, granules, supergranules. You don't have a continuous, spatial scale. Yeah, so we don't know. I mean, even the upper limit, like the giant cells in the sun, people are still looking for giant cells. That's the biggest size cells. So the supergranules are about 50 arc second. So with the chromosphere, you will see mostly the supergranules. So we worked with the supergranules sizes primarily from the calcium. So the calcium guy have a lot of importance. And then, so I was just saying that somehow, this is again another interesting thing. In the past, famous people were there. I mean, Professor Shivaraman. He worked with some people in the US and all his life only on white light. Professor Jagdev Singh has worked only on calcium. He never looked at white light data. They were never interested. Actually, white light data was all lying almost, I would say. Then H alpha also very limited thing. So people were not really doing multi-wavelength. So this has come more recent times, the importance of multi-wavelength. Then only you can build a complete story, the entire atmosphere and connecting with the dynamo and all this. I mean, this integration is very, very important. So in a way, this particular field has a lot of these elements. So I see a lot of guys who work on pure theory also are very much interested in this kind of data. This is what I wanted to also emphasize here, because the other day we were talking about even our data archive, ARIES data archive. You see the transformation has happened. See, our thing is all ARIES now.
It's all running into data. Beat anything.
No, I'm saying my language. Whenever I
He meant something else. He meant when previously when he says we or our, he meant IIA.
See, I can't avoid it because I'm almost born and brought up with IIAs. What I was trying to say is that we developed a digitized archive based on Java and PHP and so on. But then Kosov came from IUCAA because they are hosting a lot of this, data thing in IUCAA. Although the data is all hosted in IIA only, but the framework based on this, Python Flask framework, he has developed it, and he just installed it in our server. So I was just saying that why to repeat all this exercise in a number of places? We can collaborate with these guys, and we can build our data archive here pretty easily. So 1.3 is one data source you can think about because you have a reasonable length of this. But if you have any other data sources also you want to try out, we should talk to these people and get it implemented. It needs minimum resources actually. And this is the future. In fact, this is all part of the NKN stuff. So government will also very much like it. So we should try to, integrate things rather than, every other corner. So for Sangeeth particularly, I can put you in touch with these people and see where all our, current data is there from ARIES. And that's it. So this is the data archive. You can see this. That's again a little older picture. I have a more recent picture here. So in the current picture, you could see Vibhuti, you can identify who is here. He's primarily working on this. So far, he has worked on white light. Now he's stepping into calcium. This is Leh. So we had this summer school last year. Yeah. So it's actually beyond Leh. So we went for a one-day tour, and during that time, this picture was taken. This fellow, again, a MTech, integrated MTech student, Harsha. He started working, but since I moved here, I'm not supervising him anymore. I just changed the guide. One or two, Ritesh decided to travel with me. Harsha didn't want to. I didn't, of course, ask or force anybody. So Ritesh is working on CMEs, primarily in Aditya. This fellow, people refer it as a Gaussian. He's 6'3". So he also works on CMEs. He was very keen to come here, but unfortunately, his medical condition, he has a very high, powerful eye. Power in the eye. So apparently, his doctors said that the cold may not be very suitable for him. I do not know. So his parents got very scared. But he will come. Now he's in Kolkata and lockdown is over, means he's going to come here. Shubhama is in US now. Vishnu is again another MTech student. So this is interesting, some of the engineering students also chose to work with me, though I have no engineering background. But some of them felt that what we do can be useful for their career as well. And Manju is here. He's full-time for the digitization project. I have a DST project, so he's had on that. So a lot of work on H alpha. He has primarily worked. So I've not, presented the H alpha stuff there. And Vishnu also is working on some Aditya related stuff. So that's the team. So here, this is Kostu and the Ayuka team, who has developed the backend instruments. Okay, I've gone for pretty long period. Maybe I should escape and find out remotely who wants to ask what questions. Okay, I mean, I will also, you have to moderate the questions, I guess. I can do it. You want to take the questions first from the local people? Okay. So if you can hold on, people connected remotely, we are just taking questions from local residents here, and then we'll take the remote.
I have a question.
Yeah.
So we have been observing in HLFAR since long time, 6-inch telescope.
Yeah.
But most of the paper comes from the space data, right? So we have an archive which is unused.
Now, I do not know whether you have an archive. I mean, this terminology.
Data is up somewhere. Terabyte of data.
So as far as my knowledge goes about the data, because I have not seen the data, I would love to see the data some stage. But as far as my knowledge goes, this is not a synaptic observation. What they have observed from here is flares. They have not been interested in this long-term term. No, I don't think. Yeah. So you see, sun also gives away a lot of explosions and all that. So the interest here primarily has been focused on this flare observations. But since you asked this question, what is happening now in modern day solar physics is it's multi-wavelength. If you take only observation in one wavelength, it's not sufficient. So the space data is freely available, and particularly solar data is all available from next day. Next day it is available. So because of the quality of the data and the data availability, it is quite imperative that you use that data and supplement with your local observation, because you have to have something with you which others do not have. So people in the past have utilized that also. I do not work in that style. Even if I observe something here, I will make it public. But it is in the past, it has not happened. Most of the ground observatories have operated that the data which you observe is for you only. I mean, no harm. I mean, no sort of anything negative about this place. Everywhere, ground-based observatories across the globe, ground-based facility data to make it public and all that is more demanding, because you also have to have the processing routine, because you do not know, actually the others do not know what are the difficulties of your calibration methods and all that. So the ground-based facility individuals have spent much time on the data pipeline development, to make the data easily usable by others. They have not, and that's been a tradition and it's a history. It's not for this place, everywhere. I mean, in the Western world also. But now it is changing. Why I'm mentioning this, DICIS is the now new largest solar telescope in the world, which has just got the first slide. It is going to operate in a service mode. Observers do not need to go. Now, because it is just getting the first light and all that, they have some data policies for PhD students and all that, some lock-in period, 6 months and so on. But from the day one, data is archived, because the data volumes are of terabyte size. Every day they're observing terabytes of data. It's not easy to even download it and so on and so forth. So they will have some mechanism to send you tape and all that as well, because it's really, really large volume. But the data will be public. Again, NSF has put this condition. NSF, when they funded the project, they gave this condition that it has to be public. I tell you, I'm involved with a mission called Punch. it's a MIDEX mission, which will come. I mean, we did have a 3 whole night, symposium last week. NASA has made it so much particular. Now it's going to be launched in 2024. So much of work is happening with the data pipeline. You won't believe it. The simulated data have been given to the modelers now. Simulated data. That ऐसा data आना है. Instrument team is simulating the data and the data है.
I think similar policies for LSS.
So I think it is coming now. It is coming now. It's good for the community, good for the utilization of the resources and so on. Yeah. Yeah. In fact, there is a. We have actually faced. I have personally faced a lot of, remarks or criticisms also from our seniors and so on at the department. With all due respect to them, I have paper publish करता है. मेरे बहुत सारे लोग ऐसा बोलते थे. So, my standard answer would have been, if the data is public, you can also download and publish. I published 10 papers and you publish 1 paper. That's the difference. So, nobody is stopping you to, download the data and publish. In my opinion, it is more demanding, because unless you have certain, own ideas, the same data is available with a number of people. I'm just not plotting the light curve, so that way, I think there is a merit and demerit both. So I think, but at the same time, I think the mutual respect is also necessary for the people who maintain facilities. It's challenging. So there should be some way of rewarding that also. If you think that 10 years I have worked for a facility to build, and then I have not published much during all this period, and now there is an opportunity, I will take few students and I will publish. Somehow that attitude, if that person has, I think that has to be reviewed, or management has to see that whether it is justified or not. It may be justified in some way. If he has been already recognized for his efforts for last 10 years, then there is no problem. That person will not bother about it. But since it is always linked with, publications and, how many students you have and these, that, it has been a challenge. So people have been too self-centered and are sort of possessive about, I would say, things. So I think it's a responsibility of the system also to very much recognize the people who are working for building a facility, and how to protect them. How to protect them. Those individuals who are maybe not publishing that much, but they're also working hard.
Actually, it is not that effective. Particularly if you talk about this archival things, 104 centimeters.
Yeah, on the remotely as well. Yeah.
104 centimeters.
So are there specific questions on the talk? Facebook में भी question है? बापे. Okay. So can you read that out for me? Greetings. Greetings. Any correction between magnetic field and flare occurrence periodicity? Correlation, not correction. Okay. Of course, flare occurrence periodicity, as you mentioned, if you are linking with that, there are certain reports that there is some 131 day periodicity in terms of the flare occurrence, and that is also seen from sunspot area or sunspot number series as well. So obviously there is a correlation, but how strong the correlation is and so on and so forth is not very well established, because of the same fact that the flare data doesn't go back to all the 100 years. We have much longer, sunspot area, sunspot number series than the flare series. So if flares are observed with the same instrument for a very long period of time, and again, what you call by a flare, that definition is also there, right? There are different classes of flare. So that is dictated by which wavelength you look at. if it is a ground-based white light flare, then, there are certain threshold. If it is a X-ray, different classes flare, there is certain differences. So if you have a consistent, data, I mean, same type of flare from the same instrument you are working for a very long period of time, then probably you can do this, correlation study much better. But of course, there is a correlation. It's quite obvious. Yeah.
The next question is from Harshita Gandhi. Why peaks in sunspot area were resolved in 2 or 3 peaks?
Yeah. So this is the so-called double peak behavior. So I tried to explain in my one of the slides here. I'm not sharing the screen anymore. The screen is there here still. What I tried to sort of impress on you is that so the magnetic polarities in this particular plot, if you can see it slightly, let me make it slightly bigger. Here, that one polarity is the leading polarity goes towards the equator and the receding polarity goes towards the pole. Now, these blue lines, if I just focus on these things, so typically for this phase of the solar cycle, it was expected that always that blue polarities will go towards the pole. But suddenly we see for probably few months, there was a opposite polarity fluxes which were going on the opposite direction. So that is reflected here in the lower plot. If I see the north polarity is shown here, it was reducing, but then there is a flattening here. And similar thing happened in the southern hemisphere as well. In the southern hemisphere, you see this circle corresponds to the thing where this blue, surges. So we call it is actually polar surges. And this polar surge is resulting into the dip of the polar field. And that will get manifested in the next cycle in the sunspot area or the number series. So that's source of the double peak.
Again, Harshita Gandhi.